Okay, let's unpack this. Imagine for a moment that you are tasked with the impossible. You have to teach a computer to understand English.
Mhm.
And I don't mean just recognizing keywords like pizza or order. I mean actually understanding the structure, the nuance.
It is the absolute holy grail of natural language processing, or NLP. It's the difference between a chatbot that feels like a robot
Mhm.
and one that feels, like a person.
Right. And historically, you've generally had two very different roads you could take to solve this. Road number one is the, let's call it quality approach.
Okay.
You sit down with a team of linguists, people with PhDs and infinite patience, and you handwrite every single rule of grammar. You build it perfectly brick by brick.
Which is incredibly precise. It is beautiful, actually.
Yeah.
But it is also painfully slow and incredibly expensive to produce.
Exactly. Or you take road number two, the quantity approach. You forget the rule book. You just feed the computer a billion sentences and let it guess the patterns.
Which is fast, it's scalable, but it's often messy. It lacks that deep logical consistency. It's the classic tension in the field, handcrafted perfection versus statistical brute force.
And usually you have to pick a side. But today we're doing a deep dive into a paper that asks, why not both?
We're looking at a fascinating piece of research. It's titled An Unsupervised Approach for Linking Automatically Extracted and Manually Crafted LTAGs.
And that's by Hisham Faili and Ali Basirat.
Right, from the University of Tehran and Islamic Azad University.
And their mission is, it's audacious. They want to build a bridge between these two worlds. They want to link a handcrafted grammar system called LTAG with a high-speed automated one called MICA.
And if they pull this off, they basically solve one of the biggest bottlenecks in the field. You get the lightning speed of the machine with the deep semantic understanding of a human expert.
It's like putting a Ferrari engine inside a tank.
That's a great way to put it.
So let's get into the weeds on this. We have two main characters in this story, LTAG and MICA.
Sounds like a cop duo.
It really does, but they're grammar parsers. Let's start with LTAG. What is it?
So LTAG is the veteran. It's the artisan in your analogy. It was developed at the University of Pennsylvania starting way back in 1990.
Okay.
It is based on a formalism called lexicalized tree adjoining grammar, or LTAG for short.
Lexicalized tree adjoining grammar. That is a mouthful. Let's pause on that jargon for a second. When we say trees here, we're not talking about oaks and maples.
No, definitely not. In linguistics, a tree is a diagram of a sentence structure. So imagine a simple sentence like, the cat sat on the mat.
Okay.
You can draw lines connecting cat to noun, sat to verb, and show how they nest inside each other. That structure, when you draw it out, looks like an inverted tree.
Got it. So LTAG is a collection of these trees.
Exactly. But
Yeah.
because it was handcrafted by human experts, these aren't just simple diagrams. They're incredibly rich. There are exactly 12,226 elementary trees in the LTAG system.
And each one of those acts as a domain of locality. That sounds like real estate.
In a way, it is. It means the tree captures everything that belongs together in a local neighborhood of the sentence. It specifies the syntax, the grammar, but also the semantics, the meaning.
So it knows what things mean.
It knows that if you have the verb eat, you probably need an eater and something eaten. It handles those dependencies perfectly because a human designed it to do so.
So it's smart. It's the professor who knows exactly how the language works. What's the catch? Why aren't we just using LTAG for everything?
The catch is the cost. Not money necessarily, but computational cost. Parsing, which is the act of analyzing a sentence using LTAG, is incredibly expensive.
How expensive are we talking?
Well, the parsing algorithm used, a chart-based head corner algorithm. It has a time complexity of O of n to the 6th power.
Oof. Oof. Oh, n to the 6th. For anyone who hasn't looked at a big O notation chart recently, let's put that in perspective.
It represents exponential growth and not the good kind. If you have a sentence of length n, the time it takes to process it grows to the power 6.
So let's use real numbers. If I have a sentence that's, say, 10 words long.
10 to the 6th is a million operations.
Yeah.
That's manageable for a modern computer.
But if I double that sentence to 20 words, just a standard medium-length sentence.
20 to the 6th is 64 million operations. You doubled the sentence length, but the work went up by a factor of 64.
Wow.
And if you go to 30 words, you were in the billions. It is simply too slow for any real-time application.
That is a deal breaker. And I assume, because it's handmade, it's a bit brittle.
Right. It suffers from the sparse data problem. Humans can't write rules for every weird slang term or strange sentence that pops up online. LTAG is brilliant, but it's sheltered.
Okay, so that's LTAG. Brilliant, deep, but slow and a bit out of touch. Now let's meet the challenger, MICA.
MICA stands for Marseille Nan REA, Columbia AT&T. It's a dependency parser from around 2009. Think of MICA as the industrial factory.
The mass production line.
Precisely. MICA uses an automatically extracted LTAG. No one sat and drew these trees. They fed a computer the Penn tree bank.
Which is a huge database of sentences that are already parsed.
Exactly. And they use statistical methods to just rip the grammar rules directly from the data.
So it learned by watching.
Yes. And the scale difference is huge. Remember, XTAG had about 1,200 trees.
Yeah.
MICA has a massive 4,700 elementary trees. It covers way more ground.
And speed. I'm guessing it doesn't have the n to the sixth problem.
Not at all. Lightning fast. It works with standard probabilistic parsers. It can chew through text at web scale without breaking a sweat.
But, and there's always a but with the fast option.
It's shallow. It's missing the soul. Emma is great at saying this word is likely a noun or this pattern usually follows that pattern.
But it doesn't know what it means.
It lacks that deep semantic representation. It was auto-extracted, so it doesn't have those rich feature structures that the human experts put into XTAG. It just knows what the sentence looks like.
So we are stuck. We have a fast parser that doesn't understand deep meaning and a slow parser that understands everything but takes forever to finish a paragraph.
That is the state of play. And that is where Faley and Basrat come in. They asked, can we use MICA to parse the text, because it's fast, and then somehow map that output onto the XTAG structures to get the meaning?
It's like using a cheap, fast translator to get the rough draft, and then having a magical filter that instantly turns it into a perfect manuscript.
That's a very evocative way to put it. The goal is to maximize the probability of getting the right XTAG tree, given that we've seen a specific MICA tree.
But you can't just tape them together. MICA trees and XTAG trees, they speak different languages.
Correct. You can't just build a simple lookup table. It's too complex. So the researchers treated this as a sequence tagging problem.
Sequence tagging. Walk us through that.
Okay, imagine you have a sentence. MICA parses it and gives you a sequence of MICA trees. That is your observation.
Yeah.
The thing you can see clearly.
Right.
But what you want is the corresponding sequence of XTAG trees. That is the hidden state.
This sounds like a job for a specific type of statistical model. I'm getting flashbacks to college stats classes.
You're thinking of hidden Markov models, or HMM.
The HMM, the classic weather analogy, right? We're in a windowless room, but you see people coming with umbrellas, so you infer that it's probably raining outside.
Exactly. The umbrella is the observation, that's the MICA tree. The rain is the hidden state, that's the XTAG tree. You're using the visible thing to statistically guess the invisible thing.
So they built an HMM where the MICA trees predict the XTAG trees. Sounds straightforward enough. So why a whole research paper on this? Why isn't this just standard practice?
Because HMMs are notoriously difficult to train properly in this context. To train an HMM to teach it the probabilities, you usually use an algorithm called Baumwelch.
Baumwelch.
And it's an iterative algorithm. It guesses, checks, adjusts, and repeats. It's like a hiker trying to find the highest peak in a mountain range in the dark.
I like the hiker analogy.
But the problem is Baumwelch is greedy. It just climbs the nearest slope it finds. It finds a local optimum, a pretty good peak, and stops.
It thinks it's at the top, but it might just be on a small hill while Everest is right next door.
Precisely. If you start the training with random guesses, the model gets stuck on a mediocre answer. It learns a relationship between MICA and XTAG, but not the best relationship.
Exactly. And this is the core innovation of this paper, the secret sauce, if you will.
Right. They realized that standard training wasn't enough. They needed a way to give the hiker a map before they started climbing.
So they needed to initialize the model intelligently. How do you do that without manually writing the rules? This is an unsupervised approach, after all.
They developed a specialized expectation maximization, or EM, algorithm just for the initialization phase. They created what they call an initialization database, or IDB.
And what's in this database?
It's a set of sentences, about 40,000 of them, that have been parsed by both parsers independently.
Wait, but you said XTAG is slow and produces like 50 possible trees for one sentence because it's ambiguous.
That is the tricky part. MICA produces one best guess tree.
Right.
XTAG produces a whole forest of possible trees. The researchers didn't know which XTAG tree was the right match for the MICA tree.
So they have one clear signal and a bunch of noise.
Yes. So they used this specialized EM algorithm to filter that noise. They look at compatibility scores. They essentially ask, okay, across these 30,000 sentences, every time we see this MICA tree, which XTAG tree tends to show up in the pile?
They are looking for the fingerprint, a statistical match.
Exactly. They looked at weighted counts of bigrams pairs of trees next to each other. They're calculating all these probabilities to statistically align the two grammars before the real training even starts.
So they're not starting at the bottom of the mountain. They're starting at base camp right below the peak.
That's the idea. They avoided the local optimum trap by scouting the terrain first. It's very clever.
The theory is one thing. Did it actually work? Did this smart initialization actually make a better translator?
They put it to the test using 3 very different data sets: ATIS, IBM Manual, and the Wall Street Journal.
Ah, the standard NLP gauntlet. You've got ATIS, the Air Travel Information System.
Which is all short transactional stuff. I want a flight to Denver. Average length is about 11 to 13 words.
Then the IBM Manual, which is dry. And then the final boss, the Wall Street Journal.
The heavy hitter. Long, complex sentences, average length 21 words, full of metaphors, financial jargon. It is the ultimate stress test.
So what were the results? What are we measuring here?
2 things. First, lexical agreement. This is the basic sanity check. Did the model assign a verb tree to a verb? They nailed that. Around 90 to 91% accuracy. But the real test is tagging accuracy. Did the model pick the correct complex X-tag tree for the whole sentence?
This is the number that matters.
To give you a baseline, previous attempts at this, referenced in a 2010 paper by the same authors, hit a ceiling of about 82% accuracy.
82% is, okay, it's a B minus. You wouldn't trust it to drive your car.
Exactly. With this new EM-based initialization, they jumped to approximately 88% to 89% accuracy.
That's a 7% jump. In machine learning, gaining 7% on a mature problem is massive. That's the difference between experimental and production ready.
It really is. And there's a detail in the results that I found absolutely fascinating. It has to do with sentence length.
Okay, because usually longer sentences just mean more errors.
Right. You'd expect the Wall Street Journal performance to tank compared to the short airline queries. But they broke the test sets into P1 sentences under 20 words and P2 sentences over 20 words. The accuracy for the long sentences in the Wall Street Journal was almost identical to the short ones, 88.9% versus 88.3%.
Wait, really? The long, complicated sentences were just as accurate?
Effectively the same. That is wild. It suggests the model is incredibly robust. It didn't just memorize short phrases. It actually captured the underlying structural relationship.
It doesn't get confused just because the sentence drags on.
No. That validates the whole initialization theory. If it was just guessing, it would fail on the long stuff. They even included a graph in the paper showing the model's confidence over time.
And it showed the difference.
A huge difference. The EM initialization starts high and gets higher. The random initialization starts low, climbs a bit, and then just flatlines, way below the expert model.
It's proof that how you start learning matters just as much as what you're learning.
Especially in unsupervised learning. If you don't give the machine a compass, it will just walk in circles.
Okay, so let's zoom out. We have successfully turned a translation problem between 2 computer grammars into a statistical guessing game that works 89% of the time. What does this unlock?
It connects back to that original dilemma, quality versus quantity. By bridging these, we effectively upgrade the Mica parser. We can now use Mica to process the entire web at high speed.
And instead of just getting a surface-level scan, we get the X-tag quality. We get the deep semantic meaning for the whole internet.
Exactly. We get the meaning at the speed of the math, and it solves the sparse data problem for X-tag. Since X-tag was handmade, it was limited. Now it can borrow the statistical robustness of Mica.
It's like X-tag finally left the ivory tower and learned street smarts from Mica.
And this ripples out. Take something like VerbNet, for instance. It's a massive lexicon of verbs. By linking these X-tag trees to VerbNet frames, we can extend the coverage of VerbNet. This makes machine translation better, information retrieval better. It's all about connecting these isolated islands of linguistic data.
It really feels like we are watching the industrialization of meaning. We are taking this artisanal, handcrafted understanding and scaling it up to factory levels without losing the quality.
That is the goal. And doing it in an unsupervised way where the machine figures out the mapping itself is the only way it's scalable.
It is impressive work, but I have to say, there is a thought that sticks with me here.
Go on.
These researchers achieved nearly 90% accuracy. But they didn't write a dictionary. They didn't tell the computer tree A means tree B. They just fed the computer the structures and said, find the pattern.
It validates the idea that there is a universal structure underlying these formalisms. Even if Mica and X-tag look different, they're describing the same reality of language.
Right. And it makes me wonder, If computers can align their own internal languages, Micah and XTAG this effectively without us just by looking at the math, what nuances of human communication are they currently seeing that we haven't even defined yet?
That's the black box problem.
Exactly. We're looking at the hidden state behind the observation, but maybe the machine is seeing a hidden state that we don't even have a name for. If they can find the bridge between two grammars so easily, what else are they finding in our language that only they can see?
That is a question that might take more than a hidden Markov model to answer.
For sure. But it's something to chew on the next time you talk to a chatbot, and it understands you just a little bit too well. That's it for this deep dive into the architecture of grammar. Thanks for listening.